Так. Ну, давайте я попробую как-то закончить предыдущий рассказ. Ну, или какую-то мысль выделить, чтобы было понятно, как вообще это все связано. Ну, кратко, что нам говорил Андрей. А, Андрей говорил следующую вещь. Вот у него был такой оператор, или ту, равный у. Тут была единичный оператор в спинорном пространстве, а вот эта единичка, ну, фундаментальном. Вот был такой оператор, и он действовал. Так, ну, я его обозначение, правда, не помню. Ну, давайте поставим тут нолик. Нолик будет обозначать, что L0 от U у нас действует из V0, V, V0, V. Где у нас V0, это будет спинорное пространство. Ой, я начала говорить по-русски. Ну,
Если можете переключать, смотрите как.
Смотрите, как вам.
я по-русски лучше, конечно, говорю, но могу попробовать. Но это будет дольше.
Ладно, я слышал, по-английски вы лучше говорите, чем по-русски.
Ну ладно, окей. Так, сейчас. So Andrei defined the L operator acting in a tensor product of two spaces. The first one is Spinor space, and this I don't know how to say. Okay, but
The fundamental space,
fundamental space.
TM.
Okay.
I guess it's n-dimensional.
N-dimensional.
Because
Yeah.
you have subscript n for identity matrix.
Yes, n-dimensional. And then he tried to solve L equation. Наверное, сейчас у меня V0. In two Spinor spaces and one vector space. A fundamental space. So in this tensor copy. And the answer was the following. So I write this RL equation. And the R matrix, the answer for R matrix was something like this. I tried to write it. It was at the end of the previous talk. And this our matrix acts in two copies, two tensor copies of Spinor spaces.
Masha, is it important for you lower and upper indices?
When I write lower and upper indices, I assume that there is summation over these indices.
Ah, okay. But actually, this is the same gamma with subscript or with superscript.
Yes, no.
Mm.
Yes, only for summation by this a
Okay, I see. Thanks.
a's. I don't want to write these coefficients exactly. Andrei wrote this formula, but it's important that they these functions obey recurrent relations. So the following relations. So from my point of view, this was the end of Andrei's talk.
And D is equal to N.
Кто? Си?
D in
D?
denominator. U plus D minus 2.
Yes, D is
Dimension.
dimension of yes. Maybe it's better. I will use D. So
Okay.
maybe here. So yes, the dimension of Spinor space is 2 in power G halved. Okay. So in my talk, I was going to prove that these are matrix so this thing is our matrix, so it satisfies the Yang-Baxter equation. Andrei showed that this satisfies this RTT equation or equation, and but he said nothing about Yang-Baxter equation for this. So the aim to prove Yang-Baxter equation for this R matrix. So to prove this thing.
Маша, пардон, пустое место. Aim. После aim надо написать is.
Okay.
The aim is to prove.
Хорошо. Спасибо. Так. And this equation is in V0. Maybe it's better to write without any indices 0. I don't remember Andrei's notations.
Masha, sorry. Often we write quantum Yang-Baxter as R12, R13, R23 equals in other order. But here we have 1, 2, 2, 3, 1, 2.
It's in a great form if you want to you need to multiply by permutation, I think.
Yeah,
If you want to another so it's Yang-Baxter equation in great form, but if you for example are I think like this, then you for R it's Yang-Baxter equation that you mean.
So we're going to prove that written R matrix for RLA satisfies quantum Yang-Baxter 1, 2, 2, 3, 1, 2, yes?
Yes.
Okay, thank you.
But if you multiply it with the permutation, it will satisfy standard. What you
Yes.
mean, standard form?
I can write if you want.
Well, I think just multiplication by permutation.
Okay. So now, what we need for this? Clifford Algebra. So now I'm going to explain some techniques with Clifford generators just to write this R matrix in more comprehensible way and to make our calculations easier, I think. So we need I need to explain some techniques with this Clifford generators. So what is the Clifford algebra? It's generators are gamma A, where A is from 1 to D. D, it was dimension of our fundamental space, vector space. So we have D generators and relations, and this satisfy the relations. So the Clifford algebra is a vector space of a vector space with a dimension 2 in the power d. How to say it? So this is the
2 to G.
dimension. How?
2 to G.
2 to d. Okay. So it's the dimension as a vector space, and we have standard basis. Standard basis is the following. We have one generator degree 0. So here 1. D generators degree 1. For 2, we can choose this. For degree 2, we can choose these generators. And how many we have? For different A, D, D minus multiplied by D minus 1 over 2. And for degree K, we use the following notation. AC is an anti-symmetrizer. So here we have sum over permutations in SK, in symmetric group in K elements. And here the sign of this permutation. So this notation for an anti-symmetric product of these separators. And these separators we have the binomial coefficient. So the sum is 2 to d as and the dimension is a vector space. Так, что дальше? So now we introduce the generating function for these elements. So here I use the notations UA. So the upper indices or lower indices, it doesn't matter. But here is the summation by these indices. And U and gamma anti-commute. So U A gamma B the anti-commute and UA anti-commute with UB. So this is generating function for this anti-symmetric products, and we rewrite it as so in fact this sum isn't infinite because you have only finite numbers of non-zeros products, but why I write in this way, because I want to make an exponent from this thing. It's an exponent of U times gamma where Q times gamma is the sum. So the sum U A and gamma A sum over A. And this is the same as anti-symmetrizer of exponent. So my question is it clear these equalities?
Not yet.
And why here anti-symmetrizer? So you may, for example, take this anti-symmetric product of this part and it gives the same, because two times two anti-symmetrizers. Okay, and why it's the generating
Oh,
function?
sorry. Gamma, simply gamma without any subscript. This is just notation.
Here notation U gamma is the sum. So
Okay, sorry.
I have the notation U gamma.
I did not notice.
It's the sum.
Okay, then it's clear.
Хорошо. Так. And how to obtain this this gamma A1 AK, you need to take derivatives of this generating function and put U to 0. Because this is the coefficient when A and A1 and AK are different variables. The anti-symmetrizer is the same as this, and just to take this coefficient, I take these derivatives and put all U 0. And important lemma is how to product, how to multiply this generating function. So the product of K generating functions like this. Are
What is U1, U2? It is different. It's not the same as
it's
UA,
not
yes?
the same. It's different U.
Okay. So
So you have U1 gamma. It means sum over A, U1 A, gamma A. I show it first of all for two variables. If you have two kind of use, we have exponent of U gamma and V gamma. So it means exponent. Oh, I write the sum for convenience.
V.
V, да, точно, спасибо. Что тут получается? U, A, gamma, A. Плюс here I used the Baker-Hausdorff formula.
But here it is for the case when commutator of A and B isn't center, yes?
Yes, is a constant.
Yeah. Is it obvious that it is in constant? It is a constant in our case.
Yes, because commutator of these things we just calculated. We have here U A V B minus gamma A gamma B, and if we commutate this UA, we have plus gamma B gamma A. Так, не ошиблась. Нет. And it's equal to delta AB U A VB. Да, Вадим?
Yes, okay, I get it.
That's why here we don't have other terms. So next, commutators. Так, and what we have? We have exponent. Here we have minus UA VB U minus UA VA exponent of UA gamma A. So that what we need. If we look at this formula and imagine here are two multipliers, so we get this. So I prove it for two variables, but the proof for general case is the same. We use this Baker-Hausdorff formula, and every time we have a commutator of U gamma and V gamma, it brings this this.
I think we just can use induction over a number of variables.
Yeah, so we can use induction.
And you just showed the induction step for the case of two variables.
So we have we should have here not strict inequality, but E less or equal G. You mean in lemma?
Strict, not equal. If it's equal, you have UI is zero.
Okay, yeah, I'm sorry. Yes, I get it.
So is this proof clear or not, or I need to write something more?
Well, for me, it was clear. It seems it was clear to Vadim also. then it's enough.
Two people is enough. Okay. And now let's define the two types of generators. Now I will write gamma 1 in brackets and within this index A, it means that gamma acts in the first space and A is the index that shows the number in Clifford Algebra. So now I have two different spaces, like in LL relation or Yang-Baxter relation. And these generators anti-commute. And gamma A for A. So generators of Clifford algebra. And generators of Clifford algebra. So two copies of Clifford algebra, and they anti-commute with each other. And to construct the fermionic Spinor R matrix, we need to consider tensor products like gamma 1 AK and gamma 2 AK. That what we have in the formula for Spinor R matrix. And I would like to write a generating function for this, guys. Let us write like this. This is the anti-symmetrizer of gamma 1 A1, gamma 1 A2. Gamma 2 here. And this is a anti-symmetrizer by the first applied only for the first space. And we can write like this, like anti-symmetrizer in first space of this product. but here we have a factor. So when you anti-commute this gamma, so we need, for example, this, как сказать, пронести куда-то, я не знаю уже, этого слова мне не хватает.
To move.
Ну да, move here at the beginning of this sequence, and when we have a sign, and this sk is -1 in this power. So it doesn't matter what to write here, the anti-symmetrizer in the first space or in the second. It's the same things. But I chose the first. So, and for this, we have the following generating function. Exponent so I organize these things in generating function, and that's why I have here the exponent. So lemma, the second lemma. That this anti-symmetrizer we write this this element. To prove this, consider this element and rewrite this as U A Q A1 if you remember, to obtain this thing, we take the derivative of this exponent, and the same we will do with the second item. And we need to put U and V is 0. So when we move these derivatives to the left, and we obtain why this sign vanishes. Because when we move these derivatives, we obtain something very similar with this, and so it vanishes. I think we have proved this lemma because here we have expression for this thing, and now we just need to substitute this in the formula for generating function, and that's why we obtain this lemma, this equation. Okay.
Yeah.
Okay.
Бедный Вадим, тебя сегодня всех приходится слушать. And now let us write our R matrix. We don't know that's our matrix, just denote this operator. And write it in different ways. So we can write it like this. Mm-hmm. Because of this this formula for generating function, we can rewrite it. This gives the coefficient with this power before before this power before this x to k. And introduce the notation RU x star where this star means that if we have an operator star f x, you need to put the derivative instead x and apply it to f of x and put x to 0. Yeah.
R of U X, what the last line, R of X times F of the same X.
Да. Да. the
Okay,
same.
yes, so yes, now I see. Okay.
Is it the same that Rx star Fx is the same as Fx star Rx?
Сейчас Rx star F. You mean?
Is it a commutative operation?
No. No.
Oh, why?
Hmm?
Mm.
I don't think so.
Well, it's just sum of coefficients. It is a nth coefficients of Taylor series in the first function times nth coefficients of the series of the second function and sum over all n. So it should be commutative.
Что ты говоришь, что вот так правильно?
Я говорю, что yes, because it's just sum of fn times rn, where fn and rn is Taylor coefficients. Maybe something like n factorial. I don't know.
Yeah, looks correct. Yeah.
Может быть, сейчас я что-то быстро не соображу. Может, ты и прав, но я не думала почему-то про это.
Okay, so we don't need this. Okay.
Yes, we don't need this. So we use this notation just to divide this Clifford part, and so with gamma generators, and the part with the coefficients. So here RU X is sum and in this way we see that this is the operator with some coefficients, and here we have so the Clifford, like the fermionic part of this R matrix, and it's important because it's convenient to work with these things separately and with these operators. It's like a kernel operator, and we will present this operator in integral. It's an integral presentation. And use our fermionic techniques this for these guys. So this is the plan. Just to illustrate how to work this notation, let us so we have 30 minutes, so let us examine a simple example. We try to find the formula for the exchange operator. So problem, we have these operators. it changes the spaces, не знаю, gamma, and the problem is to find P is something star in this form. So maybe somebody guess what the answer is, but I don't want to write it now. We just try to solve this problem. Okay. The lemma 3 is about that the following identities hold. Now let us prove the first one. The second is can be proved in the same way. Okay. Consider the left-hand side. And use our, I don't remember, lemma 2, lemma 2. So we use this. So I write here so here lemma 2. Okay, we can move this thing and write like this. And now, okay, I write like this. If you remember the first lemma, I show it. I explained how to multiply this generating functions. So I use the first lemma. Lemma again. And here we have so this is the anti-symmetrizer of this exponent. Because we take these derivatives and obtain this exponent. So I think we have proved the first relation. Ладно. Вадим, ты там еще это
Yes, yes. I think
Yeah.
it's proved.
Доказали мы левом 3?
Yes, yes.
Ну, отлично. Так. Now we rewrite our equation. For example, this one. Gamma 2. И so rewrite this this equation like this. Something star, and here we have gamma A, and так, вот я это переписываю, вроде да. Сейчас. Да. Что-то гамма 1, гамма 2. Yes. У меня как-то плохо получается. Сейчас. Нет, нормально. Наверное, я вот это уравнение переписываю. Так, правильно я прописала? Кто-нибудь? Вроде
No.
да. Yes.
I don't understand this.
No, we have P. It's an operator. It's P of X star this.
So we are looking P in this way.
Yes, we are looking
Okay.
for this P of X.
Is it some common ansatz, or is it like any P we could write this way, or
So, for example, we will write an arm matrix in this way, and now we just want to find P in this way. Try to find.
no, I mean, Is it some common and that any like matrix can be written this way, or it have some restriction on P? Writing is it this way, yes.
I don't know. But here we can we try to do it and we can find the answer. So I don't know if any condition like this, and ну, в общем, по-русски не знаю, какие уравнения можно решить в таком виде. Ну, например, поискать там перестановку или что-то вроде матрицы, наверное.
Окей, thank you.
Ну, в общем, now I rewrite this equation in this way because I try to find P in this form. And this equation is the same. Now I rewrite our gamma 1a as a derivative of exponent. So I show these techniques because all the proof needs all this proof, the Yang-Baxter equation needs this technique. So I try to demonstrate it on simple examples just to understand. C gamma 2. So I just change this by this and this by this. It was lemma. I don't remember lemma, or just how to obtain elements from generating function.
We also should put S equal to 0, yes? In the left hand side.
Yes, thank you. And now lemma 3. So you may see it, and we will use the first relation in the left hand side and the second relation in the right hand side. What we have. Так. Так. Why it's true? So here, if we rewrite this, we use this anti-symmetrizer and put S. We take the derivative. We take the derivative by S and put S to 0. So this is the derivative in 0 point. And here the same. So is it clear? It's the consequence.
Yes, it's clear.
3. Now what we have we rewrite it in this way. All items with gamma 1 and exponent in the right hand side and the other in the left hand side and the other in the right hand side. So here we use this x of on gamma a1 and this кстати, вот может здесь твоя коммутация это как раз срабатывает то, что ты говорил, Вадим.
Yeah, I see it.
Yeah. So here we use this that px star p of x star x gamma 1a it's d something like this. So we use this relation. And what we see that they have very simple answer for this equation. It's exponent. So P is exponent of x star this is our answer, or is it the same that anti-symmetrizer of this guy, because you take the derivative. So what does it mean, this star? Here you take the derivative and put x to 0. This acts like shift, and when you put x to 0, you obtain this. So this is the answer for the exchange operator. So now I just say some words about the plan and finish. So the plan how to prove Yang-Baxter equation. Plan that in Yang-Baxter equation you have the fermionic or the fermionic products like this. And it's
Should it be different case in all three? Should it be different case? I mean,
different ways. No, okay, it may be different case. It doesn't matter. So we can K M L. Хорошо, давай так напишем. but this is the some coefficients of antisymmetrizers, and it's convenient to work with these antisymmetrizers. And so we need to learn how to multiply these antisymmetrizers. So there is a formula for some good answer for this product, and then it's fermionic part of our matrix, and after that we need to как сказать, ну, разобраться вот with this function, so with this kernel operator, and prove some relations on these operators. So rewrite it as integral operator and to prove some relation. So that's two parts, the fermionic part and this part, in some sense separately. Yes. Ну, вот как-то так. I finish.
Okay. Clear. It's more or less clear. Even the plan.
Не знаю. Ну, мне кажется, все умерли уже.
Да нет, вроде нормально. Ну,
Да,
то
не волнуйтесь, все в порядке.
Ну, я попыталась рассказать,
Если кто и умер, то все равно все в порядке.
Я попыталась рассказать, как бы, что Ляшек начал. Ну,
в общем, значительно более понятней.
не, ну, в общем, действительно, там не как у Ляшка. То есть у Ляшка вот там как бы вот эти вот сумма по гамма-А и гамма-А, это не то же самое, что тензорное произведение вот этих вот всех сумм, понятно. То есть тут как бы у нас только диагональ выживает. Поэтому у него и не получились формулы, как я понял. У Андрея. Вот когда он начал проверять. Так что вроде...
Ну,
тут...
что-то там уже расстроился, видимо, сильно и ушел. Ну, не знаю, надо ли это как-то продолжать.
Да не, по-моему, все отлично.
Все понятно. Другое дело, что сходу плохо в этом ориентируешься. Так, когда вы рассказываете, понятно, что происходит, но самому это проделать будет сложно.
Ну, это понятно. Я сама это не могу проделать тоже, даже прочитав эту статью. Ну, дальше будет жесть, потому что можно написать эту R-матрицу, ну, вот эту как бы часть, как интегральный оператор, там разбить ее на два куска, четный, нечетный, за счет представлений, как бы этих гамма-матриц. А потом там надо сильно возиться, и какие-то контуры рассматривать. Ну, в общем, там не супер приятно будет. С фермионной частью приятно, там как-то красиво. Но вот с интегральной частью будет не очень приятно. То есть я до конца не понимаю, что там происходит, но какие-то куски понимаю.
Ну, попробуем.
Ну, вот можно это разобрать. Вообще-то Ляшек собирался рассказывать. Я не знаю, как так. Я уже пожалел 10 раз. Ну,
вы можете с ним, так сказать, это там контактиться и договориться.
хорошо.
Кто из вас будет продолжать или оба?
Я догадываюсь, кто из нас будет продолжать. Если еще это будет на английском, то...
А договориться с Ляшиком — это известный результат.
Да, хорошо.